For the next little bit, we're going to go over how to do some basic mathematical operations with vectors. So, similar to the journey that you took in grade school, we're going to start with addition or subtraction. And also vector scalar multiplication. Multiplication is going to be a bit more multi-pronged. So we're going to start with just looking at what happens when you multiply a vector by a scalar. And then further on, we're going to talk about how to do vector multiplication, which takes two forms. One is a dot product and the other is a cross product. But for now, we'll start out with just vector scalar multiplication. And the third thing that I want you to be able to do is to be able to convert any vector into a unit vector. Let's just start out with addition and subtraction. So the general idea is if you have a vector, they will be described in individual components. Like in our case, if we just start with an example, let's say we have one vector that's 2x hat plus y hat plus 8z hat. So what this means is you have a vector, and then if you project it on the x-axis, you get a magnitude 2. If you project it on the y-axis, you get 1. Z-axis, you get 8. So each of these components multiplied by their respective basis vectors gives you the vector A. The next, let's say our other vector is minus x hat plus 2y minus 6z. So again, you've taken this vector and you've broken it down to 3 components by projecting them onto your 3 basis vectors. In this case, it's x hat, y hat, z hat. Now to do the addition or subtraction, you just add or subtract the individual components. So in the case of this example, add these 2 vectors together. You get 2 minus 1 x hat. So you add the 2 x components, and then you do the same for the y components. 1 plus 2 y hat, and then the z components is 8 minus 6 z hat, which will give you x hat plus 3y hat plus 2z hat. You also want to be able to do this addition and subtraction graphically in order to build some intuition. So let's just say in this case you have a vector c and another vector d. There's 2 ways that you can view it. One is you can draw a parallelogram where the 2 edges are the 2 vectors in question, and then when you draw a diagonal across it, that will give you c plus d. Another way to view it is if I again start with this c and I have d here. Another way to view it, which is equivalent but sometimes objectively easier, is you can shift these vectors however you want. So let's just shift this vector d, but what you want to do is you want to move the vectors around, which involves changing the location but not the direction, and you move it until they are all connected heads to tails to each other. So this head is connected to this tail, and then once you have all of these vectors together, you can do this for as many vectors as you want, but once they form a single chain of a bunch of heads to tails together, you just take one end, the tail, and then connect it to the head at the very end, and then there you have it. You have c plus d. So they're basically the same thing, as you can see. It's just a matter of how you want to visualize it, but it's good to just kind of have these under your belt. Now let's look at vector scalar multiplication. So in our case, we'll start with a simple example. We'll keep the same a vector of 2x hat plus y hat plus 8z hat. And multiplying it by a scalar just means that you are scaling that particular vector by the scalar that you're given. So let's say this is your a. If my scalar is, I don't know, a third, then you just change the length by 1/3 a. And to do that, in this case, let's just say 1/2, just to keep the numbers simple. If you were to do 1/2 a, so again, just shrink the length by half. If you were to do 1/2 a, you just multiply the 1/2 into each of the individual components and you're done. So that would be x hat plus 1/2 y hat plus 4z hat, and then you're done. But again, you can see there's a graphical way of viewing this, and and an algebraic way to come up with a precise answer. The last thing is the unit vector. So we've already seen some examples of a unit vector. Examples that we've seen are, examples, the y hat, the x hat, the z hat. Those are all unit vectors. And the main characteristic is that they have a direction, but the length is equal to 1. One reason you may want to do that is you might come across a situation where maybe x hat, y hat, z hat is not really the set of basis vectors that you want to project to. That maybe if you reproject your vector onto different basis vectors, the math might be easier. So in that case, these new vectors that you want to turn into basis vectors, you would want them to have a length of 1, so that they're individual units and you can write them out the same way that you describe a vector with x hat, y hat, z hat. So now that we have this vector scalar multiplication skill, you can imagine if you had a vector u, which we'll just define as ax hat plus by hat plus cz hat. The way to turn that, say this length is not equal to 1, the way to turn that into a unit vector, which is notation-wise, we just change it from this line into a hat. So u hat would just be equal to u, but you do a scalar multiplication where the scalar is the length of u. So if I were to spell out what the exact length of the different components are, it would be, from Pythagorean's theorem, the length of the vector is square root a squared plus b squared plus c squared. So then the unit vector, u hat, the unit vector version of u would be equal to a over square root a squared plus b squared plus c squared x hat. And then same thing for the remaining components. You just multiply it by the length of u. So with that, you see how you can do some basic mathematical operations, addition and subtraction, as well as we've dipped our toe in multiplication by seeing how you multiply it by a scalar. And by multiplying it by a scalar, that also enables us to generate unit vectors for whatever vector we have in question. So converting this line into a hat, basically, from a notation standpoint.